Unit 4, Motion Control, Mobile Robot Part 3, Finite State Machine. Control Design, Finite State Machine, Case Study for Finite State Machine Control. The previous two approaches, Model Plan Action Approach and Behavioral Control Approach, both will require processor, and behavioral approach may need to have multi-threading environment, and the model plan action may be require a CPU or a neural network. And right here, this finite state machine can be a simple design, just some ASIC design would be good enough. So it represents a simpler ASIC approach for control. Finite state machine, section 1. Finite state machines offer another alternative to combine behaviors. So basically we have one behavior called forward, the other one called turn. So forward a few steps and turn. So these are very simple actions. We can put them as different states. So these are states. So we basically move forward, turn, move forward, turn, move forward, turn. So these are different states. These are basic idea of having the mouse to go through the maze. And we just need these two states, but these are too simple. So we can move forward 2 feet, turn 90 degrees, and move forward 2 feet. So it will be something like this. So it may actually go into a wall. That is one problem. And we can further optimize it as move forward 40 degrees. But because you are 40 degrees, you can turn something that is 40 degrees, and you can turn one more 40 degrees. That would be becoming turning 90 degrees. So these are actually the so-called rotation. This one actually is displacement. So basically, using these two states, you will be able to approach any location, except that the grid size is actually 1 feet. Wherever you want to go, it actually is 1 feet away. You are moving on this 1 feet away locations. So you can go 1 feet, turn 40 degrees, turn, something like that, okay? So that actually is your finite state machine. If you do this, it will be 1 feet or 2 feet and turn. And that's your finite state machine if you implement this one. So something like that. You are moving according to it. So here is a state transition. So you have the state input, and you will based on the so-called forward 1 state or is turn right 40 degree state, and based on the distance to obstacle measurement to decide which one you will go. And this finite state machine is not very accurate. So we may have Python version to help it. But basically, these can solve the problem that we want to solve for the mouse in maze problem. Implementing FSM in Java, implementation behavior as parameterized function. First switch statement handle the state transition. The second statement handle the action to be taken. So this is similar to your Turtle programming if you have some experience in Python or JavaScript or Turtle programming. And this one is trying to implement simple Turtle programming to help the robots. And basically they are state transition and output, two different states. We can also use more complicated data structure for it. And this one is just a simple example. So we basically can do forward until obstacle and turn to open, two different states. So you basically will go through your maze. You will keep going until you face an obstacle, and you will turn until you see an opening. Something like that, these two states. So can hold for the closed loop feedback to the behavior themselves. So case study, here we have a simple finite state machine to locate a ball. So we have scan 360 and find the ball, then we turn. And then after we turn, we align the ball, and then we can move forward. And then we actually may align the ball again, And then we may scan again to see if where is a new ball or gate, something like that. So basically, we start from scanning and then find the ball, and we make the turn and align the ball, and then go into here, the looping back and forth. And if we lose the ball, we go to scan until we find the ball and go back and forth. Until you are very close, you go and then seek for your gate, ball gate to get out. So what if the robot had trouble correcting approaching the ball? Then we'll need to independently verify align ball and forward behaviors. So can replace random wander with one which is biased toward the unexplored region. So basically wander is a calculation of where you should go. It's a planning stage, and you can use a random number to replace it. And that actually is a control design. And this one actually is only one proposal. You can change to a different state machine, but the core computation is still the same. Still is continuing the movement until obstacle, still forward until obstacle, and turn until you see open. So it's a displacement and the rotation, two different actions. So to improve finite state machine control by replacing state with better implementation, that actually is possible. And we can also take the input data with the state in combination to generate more accurate prediction of the action that it should take and improve the control. So we have finite state machine for as the controller, and then we have IR and bump that actually is to view how far away is the obstacle. And also we have camera to see the view angle to update the plan, the model, the environment model. So we can set up some environment list. And then we can stop sensor to sense the stop thread, and stop actually will control the servo turning. And then we combine them to mapping the thread and control the finite state machine. And finite state machine will give out the control signal to drive the motor to achieve it. So basically, this portion are the sensing part. This portion will be the control part, and this portion is the actuator part. So that is what we use a finite state machine to control it. A finite state machine can be a programmable device, such as Altera or Xilinx system. It doesn't need to be a microprocessor. So it is more flexible in terms of design. And we may give you the finite state machine in Python to further discuss this different design for the finite state machine to control your robot.